Hello, everybody. This lecture is part of the OpenCAPI Big Data Analytics course on genomics. In this lecture, we will discuss how to accelerate the BWA mapping algorithm on FPGAs. My name is Zaid Lars, and I'm from Delft University of Technology in the Netherlands. And this work is based on a paper by Houtgast et al. Titled An FPGA-based systolic array to accelerate the BWA genomics mapping algorithm. This lecture will start with a little bit of background about genomics, and then we move towards this program structure of BWMM and how the different functions in BWMM look like. Then we will discuss a little bit the design space exploration that we performed in order to accelerate the BWMM algorithm. Then we present the methods and implementation and the results. And finally, we end with the conclusions. First, we start with a background about genome sequencing. In next generation sequencing, a DNA sample is sequenced into rather short trees of about 100 to 150 base pairs. And these short trees are first mapped into a reference genome to reconstruct the DNA of the sample. And then we use these reconstructed DNA to be able to identify differences between the sample DNA and the reference DNA. As the amount of data and the complexity of the analyses increases, we face huge computational limitations in our capabilities to analyze the genomics data available. BWMM is an algorithm that allows us to sequence DNA effectively on CPUs. The tool maps the short reads on the reference genome by first identifying seeds, what we call seeds, which are short stretches of exact matches between the reads and the reference DNA. After we find these seeds, we gradually extend these seeds from to the left and to the right to identify how accurate the alignment of the read to the reference DNA is. The focus of this research is on accelerating the extension part of the seeds onto the reference DNA. In the BWMM algorithm, we usually have three different functions that run for every one of these reads. The first function is called SMEM generation. In this function, we identify the number of seeds that are exactly matching the read to the reference DNA. The next function is the seed extension, and the seed extension is a dynamic programming algorithm that allows us to find the inexact matches by extending the exact match seeds left and right onto the reference DNA. And finally, the third function is the output generation function, which generates the final alignment and alignment score to the output file. If we analyze the time utilization of these different functions in the BWMM algorithm, we see that the SMEM generation takes about 50% of the time, but it's memory bottlenecks since we need to read a lot of the data back and forth from the memory. The seed extension function requires more than 30% of the time, and this function is computationally bottlenecked since it requires a lot of computation in the dynamic programming algorithm. The output generation requires about 10% of the time, which is again memory bottleneck. And finally, other parts of the algorithm are IO bottlenecks and take only 3% of the time. Since the seed extension kernel is the one that is computationally bottlenecked, it is very possible for us to be able to accelerate this function on FPGAs to make it faster. If we look at the actual way that the BWA algorithm executes the mapping of the different reads, we see that the various different threads that are running on the BWA are usually interleaved between SMEM generation and seed extension. So first we generate an SMEM, a seed in the SMEM generation function, and then we extend that seed in the seed extension function. And after all these seed extensions have been completed, we go ahead and generate the outputs in a number of different threads in parallel. In order to be able to accelerate these functions, we would like to have an unbroken long stretch of compute that we can perform on the FPGA. Therefore, we reformat the algorithm a little bit to create 3 distinct steps or stages. The first step would be totally dedicated for SMEM generation that runs in parallel on multiple threads. And then once we have a significant amount of seed generated, we copy these seeds to the FPGA, and then we perform a number of different seed extension steps on the FPGA in parallel. And after all the seed extension steps are finished, we move ahead to the output generation on the CPU. Now we discuss a little bit the way the seed extension function happens. The seed extension function is, as we said, is a dynamic programming algorithm that uses a matrix to compute the similarity between 2 sequences. Originally, it is based on the Smith-Waterman algorithm, which means that you have a matrix with inputs at the x-axis and at the y-axis, and these sequences are compared to each other. Each character of these sequences are compared to each other, and if there is a match, you will get a score for the match, and if there is a mismatch, you'll get a score for the mismatch. At the end, after the whole matrix is filled out, we trace back the highest scoring path between the 2 different sequences to identify the actual alignment between these two sequences. This matrix can be calculated on FPGAs using a systolic array. The systolic array usually contains multiple processing elements, and these processing elements, each of them calculates an individual computation, computing an individual entry in the scoring matrix. The seed extension algorithm is very similar to the Smith-Waterman algorithm. However, there are a number of small differences between the two. First of all, since we are not aligning full sequences, but we are extending seeds, there will be no initial 0 values in the matrix, like it's the case in the Smith-Waterman algorithm. In addition, in the BWA algorithm, we need a couple of more outputs in the algorithm, like the global maximum output that needs to be generated. And also we need to have partial similarity matrix calculation for the seed extension in BWA. One of the biggest drawbacks in using systolic arrays to extend the seeds in the seed extension algorithm is the fact that the seed extensions are usually too small, too short for the number of elements in the systolic array, leaving a lot of the processing elements unutilized, making the systolic array very underutilized. We can solve this problem in a number of ways. One way is by allowing intermediate outputs of processing elements to reach the final output of the systolic array using multiplexers. This is what we call variable logic length systolic arrays. Another approach is to create multiple systolic arrays with multiple sizes, shorter ones and longer ones. This is what we call variable physical length systolic arrays. And finally, we can create a large number of systolic arrays, each with individual processing elements, each of them processing a single entry in the storing matrix. In the following slides, we will discuss each of these alternatives in a little bit more details. As we said earlier, there is a drawback for having systolic array, since the reads need to travel through the whole systolic array to reach the output, even if they are much shorter than the systolic array. This incurs unnecessary latency. Therefore, the variable logic length systolic array allows us to have multiple exit points at intermediate positions between within the systolic array between a number of different processing elements, which allows us to reduce the latency significantly and allow the read, once this fully processed, to exit the systolic array in an intermediate position. The actual location for having those exit points defines how optimal our systolic arrays is designed for our specific set of reads. The other solution is having variable physical length systolic arrays, which means that we can create multiple systolic arrays on the Fpga with multiple different sizes. In this case, short reads will be processed by smaller systolic arrays, while longer reads will be processed by the longer systolic arrays on the Fpga. This allows us to have similar benefits to the variable logical length systolic array. And we can combine these two approaches together, having variable physical length systolic arrays that have multiple exit points, allowing variable logical length systolic arrays as well. If we try to identify how optimal this solution is, we identify a optimality coefficient called CO, and this is equal to 1 for the optimal solution. In the figure, we show that we have the optimality coefficient for a implementation on Fpga with 3 systolic arrays. The first systolic array has 131 processing elements, which allows us to align the biggest read possible on it. And the second and the third, the size of the second and the third systolic array is scanned in this space to allow us to identify the optimality of the implementation. As we see here, at specific regions or choices of the number of processing elements in the second and the third systolic array, we can reach rather high optimality for the implementation, reaching an optimality of 1 for a selection of systolic array sizes of 131, 104, and 67. The third alternative is to use systolic arrays with single processing elements. This creates a fully parallelized sea of cores implementation similar to a GPU on the Fpga, which allows us to have a lot of parallelism, calculating every single entry in the scoring matrix in its own core. This allows us to trade off latency for the throughput of the implementation. The challenge with this implementation is that we need to store every single intermediate output of those processing elements on chip to be able to perform the analysis effectively, which requires a lot of memory, which is usually in short supply on FPGA chip. Comparing these alternative implementations shows that we can achieve significant speed up by implementing these different approaches, achieving up to almost double the relative speed of the standard systolic array using the variable logical and physical length systolic array. However, for our implementation, it was sufficient for us to use the variable logical length systolic array, since it was enough to fully parallelize the FPGA execution with the CPU execution of the other functions. And also, it does not require any extra hardware. This figure shows the floor plan of the FPGA. The figure shows that we implemented 4 identical variable logic length modules on the FPGA. Each one of these modules requires 16% FPGA resources, which means that in total, the accelerated systolic arrays require about 70% of resources. There is still space on the FPGA for more logic, but these 4 cores were enough to fully parallelize the implementation of the seed extend on FPGA with the CPU. Comparing our implementation with the CPU implementation, we see that a single core on the FPGA is able to achieve 1.5x speed up compared to the CPU. The full FPGA with the 4 kernels is able to achieve up to 2.7 times more speed up compared to a CPU-only system. The overall design, the end-to-end implementation, achieves 45% more speed up compared to the baseline. And with this, we are able to achieve up to 96% of the theoretical maximum possible speed up dictated by Amdahl's law. In conclusions, we showed that we have designed a novel systolic array configuration that allows us to accelerate the seed extend function of BWA on an FPGA that provides up to twice the performance that is achieved from single systolic array. We showed that the BWMM with the seed extended accelerated on FPGA is able to achieve 45% improvement in performance and is able to achieve up to 96% of the theoretical maximum throughput on the FPGA. This systolic array implementation is being used in the German Cancer Research Institute, the BWA in Germany. And our latest BWMM version with more kernels accelerated is up to 3 times faster than the baseline. This concludes this talk. Thank you very much for your attention.